Okay, so good afternoon, ladies and gentlemen. I would like to begin this lecture titled Swarm Intelligence Optimization and Machine Learning. My name is Jin'no from Tokyo State University. First, I would like to thank all those involved in organizing this lecture. So, I have conducted research in various fields, including the analysis of nonlinear dynamics, neural networks, swarm intelligence optimization, and machine learning. Today, I will provide an overview of swarm intelligence optimization and discuss its application in machine learning. First, I will explain continuous optimization problems. An optimization problem is a task of finding system parameters that maximize or minimize the value of a given evaluation function under certain constraints. Such optimization problems are very important in the field of engineering. As a result, many solutions have been proposed so far. In this figure, the search range is a range given by the constraint, and the objective of the optimization problem is to find this parameter that minimize the evaluation function value within this range. The most common approach to such optimization problem is a gradient method, which searches for parameters based on the gradient information of the evaluation function. The gradient method updates parameters using the gradient of the evaluation function to find the parameters where the evaluation function reaches its minimum value. There are mainly methods like those shown here based on such gradient information. These methods are very useful when the evaluation function is differentiable. On the other hand, these methods cannot be used to search for optimal value when the evaluation function is not differentiable, or when the evaluation function is not explicitly given. Various solution algorithms have been proposed for searching when gradient information of the evaluation function is not available. Among such algorithms, there are those referred to as swarm intelligence optimization algorithms. Swarm intelligent optimization algorithms involve many agents sharing information and using this information to search for the optimal solution. Several algorithms based on the principle of biological entities acting in swarm have been proposed. Therefore, swarm intelligence algorithms include the following: ant colony optimization ACO, artificial bee colony algorithm ABC, firefly algorithm FA, cuckoo search CS, and particle swarm optimization PSO, among others. These algorithms do not require gradient information of the evaluation function to search for its optimal values. In this lecture, we will provide an overview of the particle swarm optimization algorithms, which is one of these swarm intelligence optimization methods. Now, we will discuss particle swarm optimization. Particle swarm optimization, PSO, is a method proposed by Kennedy and Eberhardt in 1995. In PSO, a large number of agents, each holding parameters of the system, to be optimized. Search within the parameter space for the parameter that optimize the value of the evaluation function. The dynamics of each agent are described by equation like the following. Like this. The vector x represents the position in the parameter space, which correspond to the parameters being searched for. The vector v represents the velocity used to update each agent's position. And p-best represents the position in the parameter space where each agent has found its best evaluation function value so far. Meanwhile, g-best represents the position in the parameter space corresponding to the best evaluation function value found among all the agents p-best. R1 and R2 represent diagonal matrix of uniform random values. Furthermore, there are two important parameters in particle swarm optimization: the inertia coefficients and the acceleration coefficient. This figure represents the contour lines of the Rosenbrock function, which is a well-known benchmark function in 2 dimensions. In this figure, the star symbol represents the position of the g-best, while other dots represent the point being explored by each agent. As illustrated by this figure, while PSO explores various points, it does not conduct a detailed search around the g-best. This fact indicates that PSO may not be conducting an adequate search for the optimal solutions. G's search range can be adjusted by inertia and acceleration coefficients, but G's values are generally set based on empirical values. We will analyze the search capability of PSO by inertia and acceleration coefficients. To analyze the effect of the inertia and acceleration coefficients, Clark and Kennedy proposed a simplified PSO system. The dynamics of PSO include uniform distribution random numbers R1 and R2, making its dynamics probabilistic. By setting R1 and R2 to a constant value of 1, we transform the dynamics into deterministic dynamics to analyze the effect of the inertia and acceleration coefficients. While there are 2 acceleration coefficients, C1 and C2, we combine them into a single coefficient for this analysis. Likewise, P-best and G-best are converted into a single parameter P by introducing a relative. Furthermore, this P is used as a reference point to convert X into Y. As a result of such transformations, The dynamics of the PSO system can be described by the following difference equation. Since this differential equation itself can be said to be dimensionally independent, we will consider it in one dimensional for simplicity. The difference equation can be expressed as the following state space equations. The behavior of this state equation can be determined by the eigenvalue of this matrix. The eigenvalue of this matrix are derived as follows. This system is a discrete time system. Therefore, if these eigenvalues lie within the unit circle in the complex plane, the system can be considered stable. In other words, the dynamics of the PSO are governed by these eigenvalues. This figure has the inertia coefficients on the horizontal axis and the acceleration coefficients on the vertical axis. This triangle area corresponds to where the eigenvalues are within the unit circle. Therefore, the area outside this triangle is an unstable region. And in this case, the search point of the PSO will diverge like this. On the other hand, in the blue hatched area, the eigenvalues are real, indicating that the search point will move toward a fixed point like this. Meanwhile, in the green area, the eigenvalues are complex numbers, which means the search point will oscillate as they converge to the fixed point like this. This determines difference equation matrix can be transformed into a canonical system using matrix P like this. Furthermore, by using matrix P to transform the coordinate system as well, a canonical determining system like the one shown at the bottom can be derived. Since it is a canonical system, this delta corresponds to the real part of the eigenvalues, and the omega corresponds to the imaginary part of the eigenvalues. So we propose such a canonical deterministic PSO. The dynamics of this canonical deterministic PSO is dominated by the eigenvalues. Furthermore, to clarify this behavior, we propose the following system. In this system, delta represents the expansion rate of trajectory within the phase space, and theta represents the update angle within the phase space. By describing the system in this way, the behavior of each particle within the phase space is clarified. Using this system, we analyze the characteristic of the PSO search point. The canonical deterministic PSO can explain the fundamental dynamics of the conventional PSO. It has been found to have global search capabilities equivalent to those of the traditional stochastic PSO. However, its local search capabilities are inferior to those of the traditional stochastic PSO. This is due to the elimination of the stochastic element to make the system deterministic. PSO fundamentally based on the assumption that good solutions are likely to be found near previous discovered good solutions, making it important to search around these areas. The horizontal axes of the two diagrams below represent the search space, with the center corresponding to the best position found. The left diagram shows the distribution of search points for standard PSO, while the right diagram shows the distribution of the distribution for canonical deterministic PSO. The distribution for standard PSO resembles a normal distribution centered around the best position, but the distribution of the search point in the canonical deterministic PSO significantly differs, particularly with a lower probability of searching near the center. To improve this distribution, we propose a new system based on the canonical deterministic PSO called nonlinear mapping optimization. The dynamics of the nonlinear mapping optimization, which we propose based on the canonical deterministic PSO, are described by these equations. The most significant difference from the canonical deterministic PSO is a formula for updating the inertial internal states. Additionally, the concept of velocity has been eliminated. Since this update equation can be considered a simple nonlinear mapping, we refer to it as nonlinear mapping optimization. In this system, the local search area can be determined by the parameter Rij, and how to search inside it is determined by the nonlinear mapping in the equation below. The nonlinear mapping that determines the search point is described by a return map, as shown in this figure, like this. This return map has two fixed points. To clarify the stability of these fixed points, we examined the slope of the map around the fixed point. The slopes of these fixed points are derived as follows, like this. The results show that the left side of the fixed point is stable because the slope is less than or equal to 1, while the right side of the fixed point is unstable because the slope is greater than 1. This means that this point can be considered a quasi-stable fixed point. In this quasi-stable fixed point, the solution first approaches the fixed point in the following manner. As a result, the system stops searching for solutions until the parameter P is alternated. To resume the search for solutions, we adjust the nonlinear map. To continue the search for solutions, the solution trajectory should not converge. Therefore, we modify the narrow area on the left side of the fixed point in this manner. By doing this, the stable fixed point disappeared, and the trajectory no longer converges to the fixed point. The horizontal axis of this graph represents time steps, while the vertical axis shows the search range. The center is equivalent to the current best position. Therefore, it is evident that the search is focused around the best position. During this process, it is critical to understand how these search points are exploring the area around the best position. Hence, we confirm the distribution of the search point. In this case, the distribution of the search point X appears as follows. The distribution is close to a normal distribution. Since the center represents the current best position, it is clear that the search can explore the area around it. Please note that this assumes the current best position, which is the center, remains unchanged while examining the distribution of the search point. This distribution is controlled by the parameter gamma. That is, parameter gamma relates to the variance of the distribution. If gamma is small, the variance of the distribution becomes smaller. Therefore, we can understand the size of gamma controls the ability of local search. If the gamma is small, the variance is small. In this case, the corresponding trajectory of such point is like this. This characteristic is related to the convergence speed. This means that also many such points are distributed near the center. They move towards the center slowly. Please note that there are situations where such behavior is effective and others where it is not effective. Furthermore, the change in these search points may appear to be periodic. However, in such process, revisiting all the already explored point is meaningless and results in poor search efficiency. Therefore, we need to consider the search points themselves. Let's consider how the distribution of such points changes depending on the parameter gamma. This graph with the parameter gamma on the horizontal axis and the search range on the vertical axis displays search points over 1,000 iterations. This type of graph is called a bifurcation diagram. As shown in the bifurcation diagram, for most value of parameter gamma, the search point fill the search range. The darker area around the center indicates that such points are denser around this region. While this diagram only covers 1,000 iterations, increasing the number of iterations will gradually fill the region with such points. This is because the search trajectory exhibits chaos, and the white stripe in the several places where gamma is larger are known as windows indicating periodic solutions. As mentioned earlier, it is desirable in such activities to cover the search range as slowly as possible, so a chaotic state is considered desirable. To clarify where the search point trajectories are chaotic in relation to the parameter gamma, we derive the maximum Lyapunov exponent, a measure of the instability of the trajectories. This graph shows the maximum Lyapunov exponent of the trajectories. Since the value of the maximum Lyapunov exponent is positive, it indicates that the trajectory of the search points are mostly chaotic. Therefore, it can be understood that the search point explores the search range without revisiting periodic points, filling the area instead. This characteristic suggests that the search can effectively cover the area around the current best position, implying an improvement in local search capabilities. To clarify the local search capability, we carry out several numerical simulations. First, as a very simple example, we apply the sphere function shifted in two-dimensional as follows. This figure shows the trajectories of the search point. The green, blue, and red dots correspond to the particle. Also, star marker indicates the current global best position, G-best. In this case, the blue particle finds the global best position, G-best. This indicates the search state. In this case, the NMO can find the optimal solution. This position is the global minimum value of the shifted sphere function. Next, we consider the case when the elliptical function is rotationally shifted. In this function, the minimum value exists within the narrow valley, like this. In this case, particles with improved local search capabilities can explore along the rotated angle, like this, enabling them to reach the minimum values. So, like this. Next, we consider the case of the Rosenblock function. The global minimum value of this function also lies within a long flat parabolic sphered valley like this. Here is a global minimum value. Unlike the previous case where the valley was straight, in this case, the global minimum value exists within the curved valley. Moreover, because this valley is very narrow area, it is generally said that searching for the global minimum value is difficult. However, particles with high local search capabilities can navigate through such curve valleys and reach the global minimum value following the path of the valley. So, like this. So, yes, the global minimum is reached to the global minimum values like this. On the other hand, the searching by standard stochastic PSO looks like this. In general stochastic PSO, there is a tendency to explore a wide range, resulting in weaker local search capabilities. Therefore, while it can discover the vicinity of the solution that is the minimum value, it often fails to find the minimum value itself. This is a last region function, which is a multimodal function. In this function, there are many local solutions, and the center is a global minimum. Here is a global minimum. In this function, there are many local solutions. This is a typical search scenario using the standard stochastic PSO. In such case, global search capabilities are more important than local search capabilities. In other words, by effectively exploring distant areas, it is possible to escape from the current local solutions. However, while it is possible to escape from these, there is no guarantee of reaching the true minimum values. This is a case where the minimum value of the last origin function is searching using nonlinear mapping optimization. In nonlinear mapping optimization, such range can be determined by the parameter Rij. Here, we are dealing with a situation where the value of Rij is small, resulting in a narrow search range for local explorers. In such scenario, because the search range of each particle is very narrow, it is not possible for them to escape from the local solution like this. On the other hand, this is a case where the value of the parameter Rij was increased in nonlinear mapping optimization. In this situation, the expansion of the search range allowed for escaping from local solutions and discovering the minimum values. Thus, in nonlinear mapping optimization, it is possible to control both local and global searches, which was not feasible in standard PSO, thereby improving the search performance. As demonstrated above, the nonlinear mapping optimization method allows for separated control of local and global search capabilities. This table shows the comparison result with standard PSO 2011. Each benchmark function is 50-dimensional. The nonlinear map optimization was able to improve solution in almost all the benchmark functions. However, the setting for parameters like Rij are still not adequate, and they need to be adjustable according to the given problems. However, such swarm intelligence optimization proves to be effective when explicit gradient information of the given evaluation function is not provided. Next, we will present example of the application of these swarm intelligence optimization to machine learning. Recently, machine learning, especially neural networks, has garnered significant attention. Among the various types of neural networks, multi-layer perceptron have been spotlighted for their excellent function approximation capabilities. The foundation of a multi-layer perceptron is what's called a perceptron. A perceptron determines its output by multiplying multiple inputs by weights, adding them together, adding a bias value, and then passing the results through a nonlinear function. A multilayer perceptron, as the name suggests, consists of the multiple layers of these perceptrons. In a multilayer perceptron, running involves adjusting the weight and bias values to capture various input-output relationship. This adjustment of weight and bias is achieved by minimizing a loss function, which is defined based on the difference between the expected output and the actual output for given inputs. Generally, the loss function of a multilayer perceptron is non-convex with many parameters. Typically, optimization of a multilayer perceptron is performed based on the gradient of the loss function. On the other hand, multilayer perceptron have a very large number of the parameters and are characterized by non-convex function, leading to the presence of many local solutions. Therefore, gradient methods often fail to reach the optimal values. As a solution, we attempt to optimize the learning process using particle swarm optimization without relying on the gradient information of the loss function. However, it is possible to obtain the gradient information of this loss function in reality. Therefore, please note that the experiments here are strictly to see what result can be obtained when searching for parameters without using gradient information. In the experiment, we use the following three types of classification problems that are not linearly separable. First, Three-dimensional exclusive OR is a problem where three inputs are classified into two binary outputs. Second, quadruple circle involved classifying two-dimensional inputs into four classes. Finally, the last one involves classifying 10 classes using handwritten character data from MNIST, which has been transformed into two-dimensional data using an autoencoder. The 10 class data using MNIST were created as follows. Input data of 10 types of handwritten digits from the 28 by 28 MNIST dataset were compressed while extracting features using a CNN, and the final classifier was trained to perform class classification using two-dimensional latent variables. In this process, the two-dimensional latent variables corresponding to each digit spread out in a radial function as shown in this figure. Each color in the data corresponds to each handwritten digit. This two-dimensional latent variable space was then used as the input for a multi-layer perceptron to create 10-class classification programs. So we conducted the experiment to train on three types of classification programs using a multi-layer perceptron. In the experiments, we compared the result of using a gradient method called ADAM, which is based on the gradient information of the loss function with those of using PSO, which does not utilize gradient information of the loss function. The multi-layer perceptron uses in the experiment was set up with 3 neurons in input layers, 2 neurons in hidden layers, and 2 neurons in output layers for for 3D exclusive OR program, and 2 neurons in input layer and 2 neurons in hidden layer and 4 neurons in output layer for the quadruple circles problem. Finally, the 2 neurons in input layer and 2 neurons in hidden layer and 10 neurons in output layer for latent MNIST problem. The loss function used was categorical cross entropy, which is differentiable, and Adam utilized its gradient information for running. In contrast, PSO used only the loss function value and was set with 16 particles. The result of these experiments are present next. These graphs below represent the classification accuracy at each epoch during the learning process. The blue line represents the learning results of a multi-layer perceptron based on the conventional gradient method. In contrast, the other three graphs show the learning progress when optimized by three types of PSO. The lighter color indicates the standard deviation for each method. According to these results, PSO showed better outcomes than the gradient method for the 3D XO problem and quadruple circle problems. But the gradient method yields significantly better results for the latent MNIST data. As the number of parameters increases, the loss function of a multilayer perceptron generally has many local solutions. However, it has recently become clear that even local solution can yield good classification accuracy in multilayer perceptron, which may explain why the gradient method achieves better results than PSO. Okay, I will conclude this lecture. Today, I had the pleasure of lecturing on swarm intelligence optimization and machine learning. There are various methods within the swarm intelligence optimization, but today I focused on particle swarm optimization and nonlinear mapping optimization, introducing a performance-enhanced version through determined nonlinear mapping optimization. I explained that in swarm intelligence optimization, the balance between local and global search capability is very important. Additionally, I discussed using PSO for training multilayer perceptron in machine learning. Finding the optimal solution is challenging due to the many local solutions represent in the loss function of the multilayer perceptrons. However, since these local solutions often exhibit good performance, the gradient method tends to yield better results than PSO, especially when dealing with a large number of parameters. That's all. So thank you for your kind attention. So if you have any questions, please ask in the chat section. Thank you for comments. I have one question. So from the Professor Toshimichi Saito. Toshimichi Saito says, how do you tune hyperparameter of the PSO-based machine learning? So it is a very difficult questions because the hyperparameter of the PSO and nonlinear mapping optimization is very difficult. Now our hyperparameter is setting by empiricality. It is my future problem of the setting of the hyperparameter of the PSO and NM. Okay. Any other questions and comments?